what happens if someone asks you to take the sine, the cosine, or tangent or something of an angle bigger than 90 degrees? So yesterday, I don't know if you even noticed, in all the questions and in the title of the lesson and the title and all that, we were doing was like acute angles. We always said that the angle we're considering is acute. Every time we said something about angles, we had to like go out of our way to say, by the way, we're working with an acute angle. Well, today we want to like consider what our lives would be like if we considered bigger angles. And right away, maybe you already have a sense of like why we would care about bigger angles. Clearly, you could come across a bigger angle in the wild, yeah, right? So if we come across an angle in the wild, we need like a way of talking to one another about that angle. So we're gonna lay a coordinate system on top of an angle in a very systematic way. We consider one side of our angle, that ray, to be the initial side, or the initial ray, and then we open counterclockwise to produce the terminal ray of the angle. So we orient the coordinate system so the origin is at the vertex of the angle, and we consider one of the rays to be like the initial ray and one to be the terminal ray. And then there is this like sense of motion also, that like we consider this like an angle in the positive sense if we're opening counterclockwise from the initial side to produce the terminal side under a rotation, right? So I think that's terminology you've used before, but it's important, I think, for two reasons. One, it helps us maybe orient ourselves as far as like how to think about what we're doing when we're dealing with like a 95-degree angle or a 200-degree angle. But also it helps me, this little like rotate idea, helps me understand what it means to have an angle bigger than 360 degrees too, doesn't it? If we have an angle like 500 degrees, keep in mind, you can't encounter an angle bigger than 360 degrees in the wild, right? But if you come across an angle, its measure will be no more than 360 degrees. So why might it be meaningful to talk about an angle bigger than 360 degrees? Shouldn't we never have to do that? And the answer is, well, if we start with this notion of like motion, and we understand this definition to include kind of like this idea of rotation in the counterclockwise direction, can we rotate more than 360 degrees? The answer is absolutely, if we now have a lens of like rotation. If that's our idea of what we mean by angles, rotation, then I think it is meaningful to talk about 500 degrees. If you're like a snowboarder, then you might want to talk about, 720 degrees, or if you're a skateboarder or something, maybe you're using that kind of language. I'm calling it alpha, whatever, it doesn't matter. Okay. If that's true, then we want to have a notion too of when angles land at the same spot, and that's the definition we're giving here, this idea of coterminal angles. That is, two angles that have different measures, but the same initial and terminal side. So we have this angle alpha, but then we also have this angle, right? That's 360 degrees bigger than alpha. And they would have the same starting place and the same ending place, it's just one might have gone around more times. Rotation is the kind of, again, the lens here we're using to describe what we mean by go around more than once. I think this is all terminology that we learned before. There was something else I was going to say about that. We good? Okay. So practice writing some coterminal angles to these angles, if you will. And you can practice your Greek letters along the way too. The first one's gamma. I think I showed you that one yesterday or the day before. It's a gamma. And the second one's beta. What's the third one? Have you seen that one before? It's not theta. Yeah, it's phi or phi, depending on how you pronounce it. Yeah. But give me an example of another positive angle that has the same terminal side, and also a negative angle that has the the same terminal side as the first one, and do the same for the others. So maybe we actually fill out a pen. Gamma. It's the third letter of the Greek alphabet. It does have a little loop in it, kind of. Depends how it's rendered. Yeah. Kind of like a little shoot. No. All right. Sounds like we're ready. Here we go. So, how about Katie give me 2 answers for the first one there.
Okay, you could do 395, or you could do negative 325.
Okay, and what are you doing there?
I'm adding 360 and then subtracting.
Okay, and you could add 360 degrees another time, or 2 or 3 if you want to. But you didn't feel like doing that. That's fine. Exactly. Perfect. Deke should help us out with B here. What's going on with beta? Sorry, say it one more time. 210. Okay, and what else? Hey, I guess you guys don't have trouble hearing her too. Go ahead, Deeksha. What else would that be? Yeah, give another negative angle maybe. What is it? Negative 510? Okay, you guys agree with those? And then we'll call them. Okay, how about Bianca? Give me C then. So did you come up with some there? 9 pi over 3? Oh, 8 pi. And what are you doing there? Can you guys stop talking? Sorry. Yeah, you're adding 2 pi, right, or subtracting 2 pi. Yeah, good. And it might be useful just to like write them all down all at once. Clearly there are an infinite number of coterminal angles to these, but we can write them all down, can't we? So let's write them all down. It's 35 degrees plus 360 degrees, or any multiple thereof, right? Where n is an integer. Keep in mind, I have really just named them all, haven't I? If n is 0, we get gamma. If n is 1 or negative 1, we get Katie's answers. And if n is like 17, we get another answer, don't we? Any positive or negative integer here will give us not just more options, but the exhaustive list of all the angles that are coterminal, right? You can do something similar on B. Down here, we can do 2 pi over 3 plus 2 pi n. So same deal, yeah. Again, where n is some integer. Right? So that gives us, again, that gives us the whole list, doesn't it? Okay, well now we're finally ready to actually, now that we've like established what we mean by angles bigger than 90 degrees, and we've like talked about how to position them in the coordinate system, it's now finally, it's appropriate to actually ask the question, can we take the trig function values of these? Can we actually find like the sine of 95 degrees? Why is it a problem using our old definitions? Yeah, if someone asks a geometry student, using the old definitions we talked about from yesterday, what is the sine of 95 degrees? Their process is, okay, well I start by forming a right triangle, with the angle you gave me in one of the corners. But if I give you 95 degrees, that's going to be problematic. Do you agree?
Yeah.
So it breaks the old definition, and yet for reasons that we haven't fully gone into yet, we would still like to be able to maybe ask the question, what is the sine of 95 degrees? Well, hopefully we'll describe soon why we want to know that maybe. But so we'll start by doing, this is why we have to talk about the other stuff first here. We'll start by putting your angle, someone brings me 95 degrees, we'll start by putting your angle that you brought me in standard position. And then, step 2, find a point of your own choosing anywhere on the terminal ray. And if you could just write down the x and y coordinate of that point that you chose, that'd be great. And then I'll just tell you, because I think this is review. I mean, I don't know. Maybe I should ask you. What is the sine of theta? I don't know. Do you know how to find this, the definition in general? It's not just opposite over hypotenuse, because remember that doesn't work anymore, right? We need a new definition. Yeah, it's the y value. We also need one more piece here, though. We need this. Distance. We need to also measure what our distance is, or rather maybe compute it using the Pythagorean theorem, right? Isn't that distance r away? Isn't that root x squared plus y squared? Let me ask again. Anyone remember the definition of sine now? For this new context? Yeah, again, we can't do opposite over hypotenuse. That doesn't really work. Somebody, I was figuring this would be a review, but maybe not. It's good. I'm glad I'm doing this. Okay. Then what is? I still need a definition for the sine, though. You can do whatever you like.
Y over R.
There it is. Someone said it. Jeffrey to the rescue. It's y over r. And if you haven't seen yet why that's, if you haven't, I assume like you went over this in out of tune, like your teacher like had a prolonged discussion about why that's a beautiful way to define it. But we'll kind of refresh your memory on why these definitions are elegant. So I'll take Lauren's approach here too, just to remind you that why these like kind of make sense intuitively too. Didn't you suggest this? This picture? Didn't you suggest this picture? Who was saying draw a little triangle? Didn't you say draw? Oh, that was you. Sorry. All right. So if we, again, this is a stretch of the imagination a little bit, but if we like say, if you come along with me, let's stop thinking about theta and let's think about this other angle. Then it's certainly true that that angle is acute, and we could answer the question from yesterday, right? What is the sine of that angle? And the answer is it's opposite over hypotenuse, because we can do that in a little right triangle. So that's great, good. But isn't opposite over hypotenuse y over r? You see how that makes sense? So that actually kind of makes sense, that agrees. What happens if we go to take the cosine of this angle using this definition, though? We get adjacent over hypotenuse for this little angle. But what's the problem with, what's the difference here? For our definition, cosine is x over r. What's true about the adjacent side, or x? Yeah, it's what? It's negative. So notice that this new definition does result for any one of these given functions in sometimes giving negative values, yes? And yet we still want to think about that as being meaningful. We'll say why that makes sense some more as we go. In the first quadrant, I want to make sure you notice that in the first quadrant we all have positive values. And so is it clear that in the first quadrant, this new definition, all of these 6 new definitions, agree with the definitions from yesterday, the old definitions? Do you agree in the first quadrant that all 6 trig functions have the same value using the old definition or the new definition when you're dealing with an acute angle? Which is, by the way, a desirable property that you should want to have for any definition you come up with. Don't you want it to be kind of backwards compatible with the old things we did? You want to still be able to talk to people in geometry and speak the same language. It's like if you're developing software, you want it to open like the old files, don't you? You don't want to like put a new piece of software out that like makes everything you used to do obsolete or something. You want backwards compatibility. And I'll just give you kind of a teaser. If you someday take complex analysis, we extend this even more. we're enlarging the tent, right? Now to include all angles, all real numbers. We're going to be able to take the sine or the cosine or the whatever of any real number. But if you take complex analysis someday, we might want a bigger tent than that. We might say, can you take the sine or the cosine or tangent of any non-real number too? Can you do that? And so whatever new definition that they're going to give you when you take complex analysis someday, better be backwards compatible twice to this definition we're just now giving and to the geometry definition that we first started with way back in the day. Right? So this is a big idea in mathematics, right? This idea of like backwards compatibility with our definitions becoming more general. All right, so give this a try. We know that letter, don't we? It's an omega. Yeah. Bryn, can you see okay back there? Okay. Like Oren doesn't probably have to be perched if you want him. Have you ever seen okay? All right, you can keep perching then. It's fine. Yeah, if you haven't done it already, I might draw, like, at least draw a little picture. You don't necessarily have to, but this is in fact the similar picture to what we had on the previous slide, isn't it? Whoa. So we're using these new definitions to figure out this. We want like the sine of omega, cosine of omega. What do you need to do first before all else? Yeah, we are going to need r. That's in all these definitions. So r is equal to something. I don't know. Square root of something, isn't it? Whatever you get. What is that? Plus 9 is 34.
Thank you, bro.
All right, and then we'll get some folks to give me all these trig function values now. Refer to the definitions again, or hopefully you know them maybe, but if you need to look them up, that'd be great. All right, so Corinne, give me the sine of omega whenever you're ready. Corinne, whenever you're ready. Where is Corinne? It's right there. Sorry, I keep finding it. Hey guys. I'm going to ask some people for these values. Just make sure you can hear them. See if this is what you got. So let's make sure we're listening again here. Hey guys, shh, go ahead, Corinne. Sine is 3 over root 34. Okay, and then the cosine is, Maria? Okay, it's something negative, like we said on the previous slide, but now we've actually put some numbers to it. Robin, give us the tangent. Tangent. Negative 3/5. Yeah, y over r, right? The cosecant, Daniel.
Square root of 34.
Good. And the secant, Allie. Say it when we get to 3 over root 34, is that what you said? 3 over root 34. 3 over, I gotta remember what secant is. That's r over x, right?
34 over 5.
Close. X is negative 5, yeah. And then Bryn. Look us up with cotangent. Good. By the way, would you have gotten the same answers if we had, because I said our instructions were pick any point you like on the terminal side. Would we have gotten the same answers if we had picked another point on the terminal ray? Give an example of such a point. Like, yeah, negative 10 comma 6, for example. Would you have gotten all the same answers? I think you would have after our discussion from yesterday, too. We just have basically kind of a similarity argument to make. Or if you're looking at the algebra, you get like a factor of 2 canceling out everywhere in these ratios. Okay, so it is arbitrary. It is arbitrary how far away you pick your point to be, right? So in fact, that's a free choice you can make. So why not choose it to be something nice instead of root 34 is the next move we're going to make. I think, Cassie, how did you suggested negative 10, 6. How did you find that? Oh, yeah, that requires that you know that there's a point on the terminal side. That's true. Yeah. And that might not always be given. Yeah. All right, so if it's really true, ladies and gentlemen, that we can pick a point anywhere we like on the terminal side, then someone must be out. Then why not choose a point that's really nice, a nice distance away, like 1? So I've got the same picture up here, but this time I've got r equals 1. I've just declared that that's my choice that I'm going to make. Which again, I hope you realize is arbitrary, but I choose 1 because it's nice. Okay, I hope you understand that. I can do that. The set of all points, listen, the set of all points that are 1 unit away from the origin form a circle around the origin of radius 1. If you're thinking about like the locus of points, if you're thinking using geometry ideas. Okay? And then the new definition, they're not new definitions, the definition we just gave, if r happens to be 1, are really nice. Like what's the cosine? I forget. The cosine is x over r, isn't it? So if r is 1, again, just like yesterday we said, I love dividing by 1, I love dividing by 1, then all these definitions get a little bit simplified if r happens to be 1, don't they? We like it. Again, it's an arbitrary choice, so why not make it easy for us? And the other important thing to notice, I think, too, is that then, if someone tells you a point, if you happen to know a point on the terminal side of your angle that's 1 unit away, then if you know the coordinates, then what are you looking at when you look at x comma y? You're actually looking at cosine of the angle you're looking at, comma, sine of the angle, right? That's like it's staring you in the face. If you happen to know that your point is 1 unit away from the origin, then you know already that the terminal side of an angle passing through there, right, what its cosine and sine are. You're looking at them. They're staring you in the face. All right. How you like that? Am I right that this is a little bit good? This is good? Is this good review? I mean, I know you've talked about the unit circle in your life before. But I want to make sure you understand why these all are very, very, very natural choices. At every turn, these are natural choices to make as mathematicians. Make sure in your notes you get 2 exclamation points at the end, okay? Did you get that? Did you get that? 3?
Sorry, I forgot.
3's okay.
Are you ready to do that?
No!
Wait, you need that? Sorry.
Sorry.
All right. So, obviously, this is like all you need to know in life about the unit circle and how to find trig functions evaluated of any angle you like. But there are a couple angles that like we talked about yesterday, that we know and kind of love, don't we? That seem to come up, that we like, and also provide like some ground, kind of a playground to talk about these ideas. 30 degrees, 45 degrees, 60 degrees. And then again, you might want to know, you might question of yourself, are there other ones I could find that these trig function values for? So I have a copy of this that I'm going to give you right now. There are in fact 16 points that we can pretty easily name around the unit circle. And my question I'm about to ask you here is, can you please justify why you know if this is 1 unit long? Hey guys, you guys just kill the side conversation. That'd be fantastic. Okay, if you know this is exactly 1 unit long and this is 30 degrees, can you just prove to me, justify, explain why root 3 over 2 comma 1/2 have just got to be the coordinates of the point at the end there? So, or, yeah, I mean, we kind of ran through that logic yesterday, didn't we? Can you justify why all the coordinates, I mean, really, my bigger question is, can you justify why all the points are what they are? Could you have made this circle yourself? I hope so. Like, I hope you could have figured out what the coordinates of all those points are without anyone telling you, even though this is a nice little handy reference. And again, let's talk about why this is useful to look at, okay? If someone asks you, what is the sine of 7 pi over 4, for example, someone asks you that, if you happen to know that 7 pi over 4 is down here, right, then, and you happen to know its coordinates are root 2 over 2 comma negative root 2 over 2, then what is the cosine of 7 pi over 4? If this really is 1 unit long, then the cosine is just, again, staring you in the face. It's root 2 over 2, isn't it? And the sine, also staring you in the face, is negative root 2 over 2, isn't it? So can someone just justify, run through again, why, did someone think about it here? Okay. Why is it that this coordinate right here, for example, root 3 over 2 comma 1/2, why is that what it is? Can you explain? Why is that coordinate half what it is? Like, if I hadn't told you that, could you have figured it out? Explain. Explain. Lauren, you want to take it away? We did the proof yesterday? Okay, so help me out, because I don't see, I remember doing something with some triangles and stuff, but I don't see any triangles here. You want me to make a triangle? That's asking a lot, but how would you like me to make it? Straight down? You want me to stop? Ever? Right there? Okay. And then what? That's one side. You want me to make another side? I think I see where you're going. Alright, so she claims that this diagram that we had this conversation yesterday, that's 1, I know, because it's a unit circle. Did we have this conversation yesterday? Why, if this is 1 and this is a 30, 60, 90 triangle, that this is 1/2? And this has got to be root 3 over 2. Did we go through that kind of proof yesterday? By the way, do you see a 60-degree, an equilateral triangle here somewhere? I see it. Boom. All right. And the same kind of argument can be made about root 2 over 2, right? Or the other ones. Great. So, how do you remember where the angles are, though? It'd be nice to kind of start getting familiar with this, because eventually the place I want to have you store this is not just in your binder, but in your head if it's not already there. So we want to make sure that this is really clear. Like if I say 7 pi over 4, how do you know it's this guy down here? Well, let's think about it. Where are all the pi over 6 ones? Let's first notice that they're all in a pretty predictable place. Right? 30 degrees off the positive x-axis in either direction and 30 degrees off the negative x-axis. We've got this one here makes sense. That's pi over 6 over here. And the others are just reflections over the x and y axes, aren't they? Kind of looks like an X-wing, right? Like Star Wars action. Low and tight to the x-axis. Boom, boom. Right there and there. Okay? Pi over 6, I remember where that one is because it's one of the ones I know and love. I just happen to remember that one. How do I remember about 5 pi over 6, though? Help me out there. Why do I know that second quadrant? That's this one. Because which one? Why, huh? Because missing a 1/6 of pi. Yeah, I like that explanation. Right? It's almost pi, isn't it? So it's just short of pi. I like that explanation. Why is 7 pi over 6 here? Why has it got to be this one? Of these 4, why is it this one? Yeah, it's a little more than pi. Yeah, and then what about 11 pi over 6? Why is, of these four, why is it this one? Because it's so close to being 2 pi. All it needs is pi over 6 more, and it would be 2 pi. That's good, okay. What about the pi over 4 ones? Those are here in red, kind of like X-Man style, right? Your favorite superhero might have this logo on his front, right? Okay. So again, same deal there. Why is 3 pi over 4 in the second quadrant? Why does that make sense? Yeah, it's almost pi again. Now I want you to start building some observations too around this. If you have 3 pi over 4, 5 pi over 6, can you see any relationship between the numbers in the numerator and the denominator? Yeah, it's like 1 less if we're in the second quadrant. So even though we haven't talked about 2 pi over 3, I know it's definitely a second quadrant angle. Even though you've never even heard of 7 pi over 8, you know that's a second quadrant angle, yes? Okay. What about the ones down here? I'll take a hand maybe. You guys are kind of distracting each other, I think, a little bit. I'll take a hand. What about down here? Yeah, go ahead. Yeah, 1 more. And then what's the trick in the fourth quadrant? Why is it definitely true that like 11, what's the relationship between the numerator and the denominator there? Yeah.
It's 2 times the denominator plus 1.
Yeah, right? So do you see that trend on all these? The pi over 3s are here. So, for example, let me see if I can at least say, walk through 1 or 2 of these before we go. I want to just run through, and again, keep in mind that eventually this is in your head, not in front of you, okay? So we'll put it in front of us just for now to remind us. But if I'm thinking about this without looking at the picture, here's my thought process when I see sine of 2 pi over 3. I think, okay, pi over 3, I know it's one of these guys, right? Boom, right? Up here or down here. Which, it's 2 pi over 3, so which one is that? Well, that's going to be in the second quadrant. I've just isolated it here. And now I need the sine of that angle. What's the big thing, isn't it? I just need to figure out what the y coordinate is. It's that big number. What's the big number in my arsenal? Oh yeah, that's right. Root 3 over 2 is the big number, I know. Done. Root 3 over 2. So that's my self-talk. What about tangent of 3 pi over 4? What will that be? Well, that's here, right? It's one of these guys. It's second quadrant, though. It's right here. And I know it's something. It's y divided by x. Something divided by something that's the same, except negative. So I think it's -1. So you get this? Root 3 over 2, -1. What about 11 pi over 6? We're going to take the cosine of that. That's one of these guys, isn't it? This one, 11 pi over 6, that's 1 less than twice the denominator. What's the cosine of that? Or, yeah, right, the cosine? Well, it's this distance, isn't it? It's the x coordinate, which is root 3 over 2. Is it positive? Of course it is, right? So root 3 over 2 is my answer there. 240 degrees is actually a little tricky for me because I like radians better now. But I can get it, you know? So this is how these feel, right? Next time I see you, we'll have a new nominee for president, right? See you on Wednesday.
Maybe I'll see you on.